Hi everyone, my name is Jason Jiang. Today I'm going to be discussing the solutions for the AMC 8 from 2017. If you have any questions as I'm explaining, feel free to unmute and ask them. Otherwise, I'm just going to go through the questions in order. We'll start with question 1. So, question 1 asks, which of the following values is the largest? So what we're going to do is evaluate each of them and just see which one is largest. So first we have 2 plus 0 plus 1 plus 7, and that's equal to 10. Next we'll look at B. We have 2 times 0, which is 0, plus 1 plus 7, which is 8. Next we have 2 plus 0 times 1 plus 7. So because we have to follow the order of operations, we're going to do the multiplication in the middle first, and that's 0. And then we'll do 2 plus 0 plus 7, which is equal to 9. And similarly on D, we'll do this 1 times 7 first, and then do 2 plus 0 plus 7, and that's also equal to 9. And finally, 2 times 0 times 1 times 7. Since it's all multiplication but there's a 0, this answer is 0. Out of all of these, A is the largest, and therefore A is our answer. Next, we'll go into problem 2. We have a pie chart showing vote distributions for 3 candidates, and the question says, if Brenda received 36 votes, how many votes were cast altogether? So what we have from this chart is that 30% of the votes is equal to 36 votes. The easiest way to find 100% of the votes will be to first figure out what 1% of the votes is. And we'll divide both sides by 30 here. 30% divided by 30 is 1%, and 36 divided by 30 is 1.2, or 6 over 5. From here, we'll multiply both sides by 100, because that gets us 100% of the votes. And 1.2 times 100 is 120 votes. So that's our answer. Next question, we are asked, what is the value of the expression square root of 16 times the square root of 8 times the square root of 4? For this problem, we're going to want to work from the inside out. So we must first evaluate the square root of 4, which is equal to 2. And then we have 8 times 2 under the second square root. 8 times 2 is 16. After we square root that, we have 4. And finally, we have the square root of 16 times 4. 16 times 4 is 64, and the square root of that is 8. So our answer is 8. Okay, problem 4 next. We have when 0.000315 is multiplied by 7,928,564, the product is closest to which of the following? And then we have our possible answer choices here. So we're not going to want to multiply these two numbers directly because it's very complicated and we only have to estimate. Looking at the answer choices, they're not terribly close to each other, which means that an estimation will probably get us the right answer. So let's first figure out what 0.000315 is close to. And what we'll find is that it is close to 300 millionths if we move this decimal point 6 times. Alright, so that would be equivalent to multiplying it by 1,000,000. So we have 300 over 1,000,000. And next we have this number. Because it's 7,928,000 something, that's really close to 8 million. So we can just treat this as 8 million. And now if we have 300 over 1 million times 8 million, let's figure out what that is. 300 divided by 1 million times 8 million. So because we're dividing by a million and then multiplying by 8 million, we cancel the millions and we have 300 times 8. And that's closest to 2,400. And that's our answer. Okay, next, on to problem 5. We have, what is the value of the expression 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 divided by the sum of those same numbers, 1 through 8. And for this, it's pretty straightforward. We're going to evaluate the denominator first and then see what we can cancel actually. That's going to be a little bit faster than multiplying all these numbers out first. So if we add up the numbers 1 through 8, we'll get 36. And now what we're going to do is see what we can cancel from the top. We see that we can cancel the 6, 3, and 2, because 2 times 3 times 6 is 36, so that cancels very nicely. And we're left with 1 times 4 times 5 times 7 times 8. The 1 doesn't matter because it doesn't affect our result. And if we group them, the 4 and the 5, and then the 7 and the 8, we have 20 times 56, which is 1,120. Okay, any questions so far? Okay, then let's keep going. Okay, we have problem 6. If the degree measures of the angles of a triangle are in the ratio 3 to 3 to 4, what is the degree measure of the largest angle of the triangle? So we know that in a triangle, the angles have to add up to 180, which means that we can represent these degree measures as numbers that sum to 180. So we'll write them as 3 times x, some variable that we don't know, 3x, and 4x. This guarantees that they remain in the ratio 3 to 3 to 4, and we also know that if we add them up, 3x plus 3x plus 4x, that has to be equal to 180. And since we can group all the x's together, that's 10x. And from here we can see that x must be equal to 18. We're asked for the largest angle, which is the 4x, which means our answer is 4 times 18, and that's 72. Next, problem 7. Z is a 6-digit positive integer, such as 247, 247, whose first 3 digits are the same as its last 3 digits, taken in the same order. Which of the following numbers must also be a factor of z? So we don't know what 3-digit number will be chosen for the first 3 and the last 3, but we do know that they have to be the same. And what that means is that if we write these, the last 3 numbers, for example this 247, as an x, then the 247 in front must be exactly 1,000 times that. So it's the same as writing x plus 1,000x, where the 1,000x represents the first 3 digits and the x represents the last 3 digits. And this adds up to 1,001 times x. Now all we have to do is see which one of these numbers is a factor of 1,001. So we'll start by doing divisibility tests now. Is 1001 divisible by 2? No. Next we'll try 3. The digits of 1001 don't add up to a multiple of 3, so we know that doesn't work. And we actually don't have to try all these. We can try the answer choices, right? If during the competition you probably want to try your answer choices first. Immediately we can eliminate E because that's greater than 1001. And then we can also eliminate 111 because 111 is divisible by 3, but we just said 1001 was not. Next, you could try 101. The closest you could get would be multiplying it by 10, and you would get 1010, and that's close, but you're not going to be able to get a perfect multiple. We can also eliminate that. Next, you would try 11 or 19. It doesn't really matter here. You'll find that 11 works and 19 doesn't. You could do long division, or you could use the divisibility trick for 11, which is adding up every other digit, and if their difference is a multiple of 11, then the whole number is divisible by 11. So as you can see, alternating digits here, you have a 1 and a 0, and then a 1 and a 0. So they sum to 1 and 1, and their difference is 0, and 0 is divisible by 11. So we do have our answer here. Okay, next, problem 8. Malcolm wants to visit Isabella after school today and knows the street where she lives but doesn't know her house number. She tells him, "My house number is 2 digits and exactly 3 of the 4 following statements about it are true. It is prime, it is even, it is divisible by 7, and one of its digits is 9. This information allows Malcolm to determine Isabella's house number. What is its units digit?" So first, if we just look at these first two statements, how many, if both of these statements were true, then there would only be one possible house number, because the only prime even number is 2. But the problem statement also says that the house number has 2 digits, and we know this is true. This is not one of the 4 statements. That could be a lie. So that means that either statement 1 or statement 2 is the one that is false, and statements 3 and 4 must be correct. So now we can check how many numbers there are that are divisible by 7 and have one of its digits that are 9, also having 2 digits. The only possibilities here are 49 and 98. Next, we just have to check which one of them has one of these statements being true. 49 is neither even nor prime, so it doesn't fulfill any of these two. However, 98 is even but not prime, so it means that it fails statement 1 but succeeds on the other 3. And that means that our answer is 98. It's asking for the units digit, so the answer is 8. Okay, next we have problem 9. All of Marcy's marbles are blue, red, green, or yellow. 1/3 of her marbles are blue, 1/4 of them are red, and 6 of them are green. What is the smallest number of yellow marbles that Marcy could have? So for this one, we're going to look at what fraction of the marbles are not blue or red. 1/3 are blue and 1/4 are red. So let's add those up first. 1/3 plus 1/4. We're going to want a common denominator of 12 here, which means that it's 4/12 plus 3/12, and that's equal to 7/12. That leaves 5/12 for the green and yellow marbles. Now, if there were 12 total marbles, meaning that there were 5 green and yellow marbles, that's not enough for there to be 6 green marbles. So we have to go one step higher, up to 24 marbles. That means there are 10 green and yellow marbles. If 6 of them are green, then 4 of them will be yellow. And finally, problem 10 here, we have 5 cards numbered 1, 2, 3, 4, and 5. 3 cards are selected randomly without replacement. what is the probability that 4 is the largest value selected? So first, we're going to notice that this is a probability question, which means that we're solving for number of successful outcomes divided by the number of total outcomes. That's our general strategy when dealing with any probability question. So let's start by solving for the total number of possibilities. We have 5 choices for our first card, 4 choices for our second card because the one we took is already gone and we know there's no replacement. And finally, there are 3 cards for the last one because the first 2 are taken. However, we now have to divide by 3 times 2 times 1. And this is because we could have picked those 3 cards in any order. And if you imagine we take those 3 cards, there are 6 orders we could have taken them in. 3 for the first card, 2 for the second card, and 1 for the last card. And that means that we overcounted by a factor of 6 because we, in the 5 times 4 times 3, we treated all 6 orders as different when in reality they're the same 3 cards. So we have to divide by 6 here. And that gives us 10 total possibilities. Now we're going to have to solve for the number of successful outcomes. We want 4 to be the largest value selected. That means that our values have to be 4, as well as 2 numbers that are smaller than 4. And how many possibilities are there for that? Well, we could pick 1 and 2, 1 and 3, or 2 and 3. And that gives us 3 possibilities. So our answer is just 3 out of the total 10. Any questions so far? Okay, great. Then let's keep going. Okay, problem 11 now. A square-shaped floor is covered with congruent square tiles. If the total number of tiles that lie on the 2 diagonals is 37, how many tiles cover the floor? And actually one of these answers got cut off, but it won't matter for us because we don't need it, right? So let's think about how we can have 37 tiles on the diagonal. Let's think about a square-shaped floor and how many tiles lie on the diagonal. For example, if we had a 3 by 3, then we would have 5 tiles on the diagonal here. If instead we had a 4 by 4, extending this, then we would have 8 tiles on the diagonal. 1, 2, 3, 4, 5, 6, 7, 8. And what you'll notice is that when our side length is even, the number of diagonal tiles is also even, because the diagonals don't share any tiles, which means that it's just 2 times however many there are on the diagonal, which is the side length. However, when it was odd, we noticed that the middle tile was shared, right? If we ignore this and go back to a 3 by 3, the middle tile is now shared, and we get an odd number of total tiles. So since we have 37 on the diagonal, that means that it has to be an odd side length. But what exactly is that side length? If we look at the number of diagonal tiles on this diagonal, it's equal to the side length. And if we look at the number of tiles on the other diagonal, it's also equal to the side length. But they share 1 tile, so the total number of tiles on the diagonal is 2 times the side length minus 1. and this is equal to 37 for us. If we add 1 to both sides, we have 2x equals 38, x equals 19, and the total number of tiles for us is going to be 19 squared, which is 361. Next, problem 12. The smallest positive integer greater than 1 that leaves a remainder of 1 when divided by 4, 5, and 6 lies between which of the following pairs of numbers? And for this one, we're going to look at these numbers, 4, 5, and 6. So we need the number greater than 1 that satisfies this. 1 is obviously the first number, and we're looking for the next one. So we want to add a number that's a multiple of 4, 5, and 6, because that way when we divide by 4, 5, or 6, we still have that remainder of 1. So next we just have to find the least common multiple of 4, 5, and 6. Let's start by finding the least common multiple of 4 and 5. Since 4 and 5 are relatively prime, meaning that they don't share any common factors other than 1, their least common multiple will just be 4 times 5, which is 20. And next we'll look at the least common multiple of 6 and 20. They share a factor of 2, so now that means that we can multiply them together, but then we have to divide by 2. So 6 times 20 is 120, and we divide by their greatest common divisor now, which is 2. We get 60. That means that the next number that works is 1 plus 60, which is 61. And I think the answer did get cut off here, but if you got the answer of 61, then you've basically solved the problem. Next, problem 13. We have that Peter, Emma, and Kyler played a chess game with each other. Peter won 4 games, lost 2 games. Emma won 3 games and lost 3 games. If Kyler lost 3 games, how many games did he win? And the key to solve this problem rather quickly is to notice that every chess game that's played results in 1 win and 1 loss. So that means that adding them up, we have to get the same number of wins and losses. So let's start by adding up the number of losses, since we have the losses for all 3 players. We have 2 plus 3 plus 3. So that's equal to 8. And that has to be equal to the number of games that are won. 4 plus 3 plus some unknown variable, right? And we can easily see that it's equal to 1. 4 plus 3 plus 1, that's 8. So our answer is B. And for the last question, if you're following along with an answer key, that did correspond to answer choice D. Next, we have that Chloe and Zoe are both students in Misdemeanor's math class. Last night, they solved half of their problems in their homework assignment alone, and then solved the other half together. Chloe had correct answers to only 80% of the problems she solved alone, but overall 88% of her answers were correct. Zoe had correct answers to 90% of the problems she solved alone, and we want to know Zoe's overall correct percentage. So we're going to want to create a table for this question. Let's look at Chloe, Zoe, and then we'll go alone or together on top. We know that Chloe got 80% of the problems she solved alone, and we know that Zoe had 90% of what she solved alone. That's a 0. And we'll make one more column here for overall. So we know that overall Chloe had 88%. And a key is that half of the problems they solve together and half of the problems they solve alone. So that means that their overall score is just the average of the percentages of the problems they solved alone and together. So for Chloe, 88 must be the percentage, 88 must be the average of 80 and some unknown variable. So we can quickly work out that 88 is the average of 80 and 96 because it's right in the middle of those two numbers. And the key here is that since they did the problems together, they must have gotten the same score on those problems. So Zoe must have also gotten a 96 on the problems they solved together. And finally, we take the average of 90 and 96, finding the number in the middle, and that's 93. Therefore, Zoe's overall correct percentage is 93. Okay, if there are no, yeah, okay. Any questions so far? Okay, then let's move on. Question 15. In the arrangement of letters and numerals below, how many different paths can one by how many paths can one spell AMC8? Beginning at A in the middle, a path allows only moves from one letter to an adjacent letter. And it's giving us one example. So here we're going to use the multiplication principle and slowly make our way outwards from this central A. So we only have one choice for our starting point, the A, and then we have 4 choices for the M. We can go in any of these directions. So we multiply by 4. Next we have to pick a C, and you can notice that from any of the M's there are exactly 3 choices of C's. So we do 1 times 4 times 3. Here's one example from 1M. And then from any of these C's there are 2 choices. There are 2 8s to pick from, for example, this way or this way. And using a multiplication principle, this is equal to 24. So that's our answer. Okay, on to problem 16. We have a figure and we're told that we choose point D on BC such that ACD and ABD have equal perimeters. And we're asked for the area of ABD. So we don't know what this length is going to be, but luckily we don't need to know it because in ACD and ABD, they actually share this length. So when we're calculating their equal perimeters, we can almost ignore that side. So let's start by calculating ACD. ACD has a side length of 3. Let's call this unknown y, and then this x. ABD has a 4, this length which is 5 minus y, and the x. So adding these together we have 3 plus y plus x is equal to 4 plus 5 minus y plus x. The x's cancel with each other. We have 9 here. Subtract 3 from both sides and add y to both sides. So this becomes 2y, and that means we have 2y equals 6, meaning that y has to be equal to 3. And 5 minus 3 will be equal to 2. So now for ABD. So now we have to add AB, or sorry, we're looking for the area of ABD, right? And since ABD and ACD share a height, that means that the ratio of their areas is just the ratio of their bases. So the area of ABC, the total, is 3 times 4 divided by 2, which is 6. That's our total. And then what we're going to do is consider that BD, which is 2, is 2/5 of the entire base. So if we do 6 times 2/5, we get 12/5, and that's the area of ABD. And there's our answer, D. And now on to problem 17. Starting with some gold coins and some empty treasure chests, I tried to put 9 gold coins in each treasure chest, but that left 2 treasure chests empty. So instead I put 6 gold coins in each treasure chest and then had 3 gold coins left over. And we want to know how many gold coins did I have. So let's use X as our number of chests because that's the unknown here. So we know that the total number of gold coins, let's call that C for coins. Okay, now let's go through the problem again. 9 gold coins in each treasure chest. 9 times the number of treasure chests. But we had 2 treasure chests left empty. So actually we only had X minus 2 treasure chests. So 9 times X minus 2, and that's equal to C. Next we have putting 6 gold coins in each treasure chest leaves 3 left over. So 6x with 3 left over, that's also equal to C. And we have 2 expressions here in terms of x that are equal, so now we can solve for x. We'll expand the parentheses and set them equal, rearranging by subtracting 6x from both sides and adding 18 to both sides. We have x equals 7. That's not our answer though. We want to know how many gold coins we had. And we can plug that into either equation, whichever one you find easier. It doesn't really matter, but the answer is 45. Whether you did 9 times 5 or 6 times 7 plus 3. Okay. Any questions? Okay. Then on to problem 18. In the non-convex quadrilateral ABCD, we have that BCD is a right angle, let's label that. AB is equal to 12, BC is 4, CD is 3, and AD is 13. We want to know the area of quadrilateral ABCD. It seems natural enough here to connect D and B, and then we have that BCD is a right triangle, so that means that DB is the hypotenuse in this triangle. We can use the Pythagorean theorem. We know that dB squared is equal to 3 squared plus 4 squared, and 3 squared plus 4 squared is 25, and that means that dB squared is 25. That tells us that dB is 5. And now, perhaps through some experimentation, we find that 5 squared plus 12 squared is 13 squared. And that means that ABD is also a right triangle. So now finding the quadrilateral area is relatively simple. We have one triangle minus another one. The area of ABD is 5 times 12 over 2, which is 30. And after that, we have this triangle we need to subtract. It's 3 times 4 divided by 2. We subtract 6. We get 24. Okay, next. For any positive integer m factorial denotes the product of the integers 1 through m. We want the largest n for which 5 to the n is a factor of this sum. So the first thing we're going to need to do is figure out how many factors of 5 there are in 98. And then after that we can put everything else in terms of 98 factorial. 98 factorial. How many of the numbers less than it are divisible by 5? Well, that's 98 divided by 5 rounded down. So this is equal to 19 if we're going to round it down. But we also have to figure out how many of them are divisible by 25, because the 25s have 2 factors of 5. So 98 divided by 25 rounded down is 3. And next we can check 125, but 98 is less than 125, so we know there are no more. And that means there are 22 here. But that's not our answer, because we have to consider 99 factorial and 100 factorial. The 99 factorial would be 99 times 98 factorial, and 100 factorial would be 100 times 99 times 98 factorial, and 98 factorial would be 1 times 98 factorial, obviously. So this is our factor of 98 factorial. And we group the 1 in 99 to get 100, and then 100 plus 100 times 99 is 100 times 100. So that gives us another 4 factors of 5 there. We know that there were already 22 in 98 factorial, and that means that there are 26 total. And the answer got cut off again, but if you have an answer key, the answer is D. Okay, so let's move on to problem number 20 now. We have that an integer between 1000 and 9999 inclusive is chosen at random. We want the probability that it's an odd integer whose digits are all distinct. So an integer between 1000 and 9999. 9999, that's all the 4-digit numbers. We have 4 spots, 4 numbers. We also know that it has to have all digits distinct and be odd. So odd is pretty useful. We can immediately know that the last digit has 5 choices here. It's either 1, 3, 5, 7, or 9. Next, we can go through the rest of the digits in any order. Let's start with the tens digit. Or actually, it's probably easier to start with the thousands digit, because the restriction is that we can't have a 0 there. So one of the choices is already gone from the ones digit, and we can't pick 0. That leaves us with 8 choices here. And now for the hundreds digit, we can't pick whatever we picked here in the thousands or what we picked in the ones. So we have 8 choices again, and then 7 choices for the tens digit. If we multiply all of these together, we'll do it out here. 64 times 7 times 5. So 64 times 35. And we'll quickly do this. So you can follow along if you haven't done it yet. We have 2,240 possibilities here, and we need to know how many 4-digit numbers there are, and there are 9,000 of those. So let's cancel a 0, and now we have to cancel all of the other common factors here. So we'll cancel out a 2 from both sides. We can cancel 2 again. And we can cancel anything else. No, there's nothing else. So our answer is B. Okay, now for problem 21. Suppose A, B, and C are non-zero real numbers and A plus B plus C equals 0. What are the possible values for A over the absolute value of A plus B over the absolute value of B plus C over the absolute value of C plus ABC over absolute value ABC? The first thing to notice is that it doesn't matter how big or small A, B, and C are, because they're always going to be equal to 1 or negative 1. Rather, we only care about whether they're positive or negative. And for that, we have a few cases. We know that the numbers are non-zero, so we don't have to worry about dividing by 0. But we can either have 2 positive numbers and 1 negative number, or 2 negative numbers and 1 positive number. We can't have 3 positive numbers because then they wouldn't add up to 0, and the same for 3 negative numbers. So now we can just go through the 2 cases and see what happens. So let's say we have 2 positives and 1 negative. Let's just say they're in order A, B, and C. That'll make it easier for us here. So A divided by the absolute value of A. We'll start with that one. Since A and the absolute value of A are both positive, this is equal to 1. Same goes for B over the absolute value of B, that's also equal to 1. C over the absolute value of C will be negative 1 because C is negative, but the absolute value is positive. And then for A times B times C, that's going to be negative, but the absolute value is positive, so we have negative 1. Adding those all up, we'll get 0. So we know that 0 is one of the possible values. And let's say you were short on time here because this is near the end of the test. We already know that these 2 answers are not possible. You could just take a random guess here. In fact, from here, you can see that this actually confirms the answer is A, because it's not possible to get 2 more values from just one more case. But we'll do the other case just to prove that you also get 0. A over the absolute value of A will be negative 1. B over the absolute value of B is negative 1. C over the absolute value of C is 1. And then ABC over the absolute value of ABC, since we have 2 negative numbers, ABC is positive, so we get 1 again. And this confirms that 0 is the only possible value. Okay, on to problem 22. In the right triangle ABC, AC equals 12, BC equals 5, and C is a right angle. A semicircle is inscribed in the triangle as shown, and we want the radius of the semicircle. So let's first draw the center of this semicircle. And now we're going to draw this line, which connects the center of the circle to this one meeting point here. We know that since the semicircle is inscribed, it meets this AB hypotenuse at exactly 1 point. And now, if we consider this triangle, let's call this point O and this D. If we consider AOD and ABC, we know that their side lengths have to be in the same proportion. The triangles are similar. And this is because we have a right angle here, as well as here, and they both share this angle. And when 2 triangles have the exact same angles as they do here, since the third one is determined by the first 2, we know that their side lengths are also in the same ratio. So now we can call this radius 5x. AD would be 12x, and then AO is 13x. But OC is also a radius, so OC is also 5x. And that means that AC, which is 12, is also equal to 18x. and that tells us that x equals 2/3. Finally, for the radius, we just multiply by 5 since we set it to 5x, and 5 times 2/3 is 10/3. Any questions for those three problems? Okay, good. Then let's keep going. Final stretch. Okay. Problem 23. Each day for 4 days, Linda traveled for 1 hour at a speed that resulted in her traveling 1 mile in an integer number of minutes. Each day after the first, her speed decreased so that the number of minutes to travel 1 mile increased by 5 minutes over the preceding day. Each of the 4 days, her distance traveled was also an integer number of miles. What was the total number of miles for the 4 trips? So we have that she's traveling for 1 hour each day. So let's just write that down. 1 hour. We have a lot of information here, so we're going to want to be organized. And each mile is traveled in an integer number of minutes. So let's actually convert this to minutes then. 60 minutes. If she's traveling in a speed that results in 1 mile being an integer number of minutes, then that means that the speed must be a factor of 60. So the speed in miles per hour has to be a factor of 60. For example, traveling at 10 miles per hour would result in a 6-minute mile. And we know that each day after the first, her speed decreased so that the number of minutes for 1 mile, this 6 here in this example, increased by 5 minutes over the preceding day. Each of the 4 days, her distance was also an integer number of miles. What was the total number of miles for the 4 trips? So we could start trying out some values. If we tried 1, 6, 11, and 16 for the number of minutes, we see that 11 doesn't work because it is not a factor of 60. And if you keep trying numbers, you'll find that they don't work. The problem here is that we're adding 5 minutes each day. And that actually means that we have to start at a multiple of 5 because we need to have a multiple of 5, right? 60 is a multiple of 5, so we're going to need multiples of 5. So 5, 10, 15, 20, and this is actually the set that works. If you had instead tried 10, 15, 20, and 25, you'll find a problem once you get to 25. So we know that 5, 10, 15, and 20 is our solution set for the number of minutes per mile. And we want to know what was the total number of miles for the trip. We know that she traveled 1 hour each day. At 5 minutes per mile, she would have traveled 12 miles. At 10 minutes per mile, she would have traveled 6. At 15, 4. And at 20, 3. And if we add these all up, the total number of miles will be 25. Okay, next. Mrs. Sanders has 3 grandchildren who call her regularly. One calls every 3, one every 4, and one every 5 days. All 3 called on December 31st, 2016. On how many days during the next year did she not receive a phone call from any of her grandchildren? So what we're going to want to do here is create a Venn diagram. And this is going to help keep us organized because we need to make sure we keep track of who calls on what day. So we have 365 total days. And for example, let's say how many days is the child calling every 3 days going to call? Well, that person is going to call number of days divided by 3, rounded down. And that's equal to 121. So let's call this the 3, 4, 5. And each circle represents the days that that grandchild is calling. So you know that the total numbers in the 3 circle will add up to 121. And we could do the same for 4 and 5. But let's start by figuring out this middle section, which is going to be common to all 3 grandchildren. For that, we need to do 365 divided by the least common multiple of 3, 4, and 5, because that's going to be the days where all 3 of them call. And since 3, 4, and 5 are relatively prime, meaning they share no common factors other than 1, we can just multiply them. 3 times 4 times 5 is 60. So every 60 days, all 3 children or grandchildren will call together. And the total number of days that happens is 365 divided by 60, rounded down. And that's equal to 6. So we have that our middle section here is equal to 6. And next, let's go to the regions that are common to 2 grandchildren. For example, 3 and 4, that's going to be 365 divided by 12, rounded down, and that's equal to 30. But we know that 6 of that 30 is already accounted for, so we only have 24 more. Next we'll do 3 and 5, so 365 divided by 15, and that's going to be equal to 24, but 6 is already accounted for, so it's just 18 more. And finally, 365 divided by 20 for 4 and 5. That's going to be 18. 6 is already accounted for, so this little region here is 12. And now let's go back to our big circles. So we have this 121 from before, but 24, 6, and 18 are already accounted for. That's a total of 48, leaving us with 121 minus 48 more, right? And that's going to be 73. Next, let's calculate for 4, 365 divided by 4, rounded down. This will be the number of days that the grandchild that calls every 4th day calls. It's 91. But we know that 24, 6, and 12 are already accounted for. So that's 42 that we have to subtract here. And we'll get 49. And finally, we have to do 365 divided by 5, rounded down. And that gets us a value of 63. Or sorry, 63. Yeah. And is that right? No, that's not right. We have 60 plus 13, it is 73. We have 18, 6, and 12 already accounted for, that's 36. So we'll subtract 36, and that means that there are 37 more. So this is the total number of days that at least one grandchild called. We want the number of days that none of the grandchildren called, so we have to add all of these up and subtract from 365. So we can do that, add up all these numbers, subtract from 365. I won't do it here, but you'll get 146. And this is going to be a pretty common type of problem. Whenever you see like this any, sometimes that'll be a good sign to use a Venn diagram, especially if you have like this every 3, every 4, every 5, this kind of problem. Okay, on to our last problem. In the figure shown, US and UT are line segments, each of length 2, and we know that TUS is equal to 60 degrees. Arcs TR and SR are each 1/6 of a circle with radius 2. We want the area of the region shown. And because these are 1/6 of a circle, we know a circle is 360 degrees. 1/6 of that is equal to 60 degrees. That actually means that we can extend these and make an equilateral triangle here, because we know these are all 60-degree arcs. And because this is equilateral and we know the radius is 2, we know these lengths are also 2. So we have an equilateral triangle with side length 4, subtracting these two arcs. So what is the area of this triangle? First of all, let's draw a height. We know that the base is 2, and from the Pythagorean theorem, we know that 2 squared plus ur squared equals, let's call this x, ux squared. So 4 squared equals 2 squared plus an unknown squared, and you can solve that. That's the square root of 12. So the total area of this triangle is 4 times the square root of 12 divided by 2, which is 2 times the square root of 12, which is equivalent to 4 times the square root of 3. And you can simplify because there's the square root of 4 in that square root of 12, which is equal to 2. All we have to do now is subtract these two arcs. We know that the area of a circle is pi times the radius squared. And we can just do that here. Pi times 2 squared is 4 pi. But because each of these sectors is only 1/6, we divide by 6. But we have 2 of them, so let's multiply by 2 now. And that gets us 4 pi over 3. So the area that we want is 4 square root of 3 subtracted, subtract 4 pi over 3. And that is our final answer, and that's B. Okay, so that's all the problems from the 2017 AMC 8. Any questions? Okay, if not, then thank you for coming, and I'll see you next time. Thank you.